Let's try another projectile motion problem. This time we're launching something from the edge of a cliff that is 44 meters high, and we want to find all of these different quantities that relate to the x and y direction. It's probably a good idea for us to not necessarily write this down for every problem, but we need to mentally check in. To the right is positive in the x direction, and upward is positive for the y direction. That is completely arbitrary in the y direction and the x direction. But in free fall, it's most convenient to choose upward to be positive, usually, because often things are launched at an upward sort of angle. And then what that means is that the acceleration, which points downward because that's the way force of gravity acts on something, then we need to make sure that that is negative. The acceleration in the x direction we are assuming is 0. It's not speeding up or slowing down in the x direction. We know that anytime we launch something at an angle, the first thing we need to do is we need to find its initial horizontal and vertical components. So if you use sine and cosine in conjunction with this 81 meters per second and this angle here of 56 degrees, I got Vxi to be 45.295 meters per second. I'm leaving a few extra significant figures in there because I don't want to round too early. Our main goal is to find delta x, which is the range. How far horizontally away will this thing land? That's what we're after. So I'm going to do 2 significant figures for that answer, but I'm going to keep some extra ones in there for these others. Vy initial, I got to be 67.152 meters per second. That is a positive number because that y velocity vector points upward, and we chose upward to be positive. All right, well, delta y is the change in elevation from start to finish for what we're doing here. And if this cliff is 44 meters high, that means when it lands at some point, it will have dropped downward 44 meters. We're assuming that this part on the bottom just continues going nicely straight and horizontal because we're not told otherwise. Well, to find the range, we need to know how long this thing was in the air. So what I would do at this point is I would use the no time equation, what I've called the no time equation, which is Vy final squared. I would use it in the y direction. Vy initial squared plus 2 ay times delta y. So that is what I call the no time equation because there's not time in it. And we're going to use it in the y direction. What do we know here? Vy initial is 67.152. So let's put that in there. Make sure we square that. Ay is negative 9.8. And delta y, we just discussed, is going to be negative 44. So we're going to get Vy final to have a magnitude of 73.293. Now, is that positive or is it negative? Because you see it's squared in the equation, so the negative sign, if there is one, kind of gets lost. Well, think about the motion of this projectile. It's going to come up, and when it hits, it's going to be traveling in the downward direction. So this is negative 73.293. Now, why is that useful? It's useful because the acceleration in the y direction is equal to the change in velocity in the y direction divided by time, which means that the time is equal to the change of velocity in the y direction. Here we go, negative 73.293 final minus initial velocity in the y direction divided by negative 9.8. You might remember that when we were talking about conceptual projectile motion problems, doing them in our head, we decided that the vertical velocity changed by about 10 meters per second every second. And so what that means is that we can calculate this projectile to stay in the air for about 14.33 seconds. And now in the x direction, x displacement equals x velocity, which is constant, multiplied by time. 45.295 multiplied by this time of about 14 seconds. And since range is what we're after, I'm going to round to the proper number of significant figures here, which is 2, 650.